Hello everybody and welcome to this presentation whose title is Recent Advances on SHM of Reinforced Concrete and Masonry Structures Enabled by Self-Sensing Structural Materials. My name is Filippo Ubertini and I come from University of Perugia in Italy. This work is part of an international collaboration that also involves Iowa State University, La Universidad de Sevilla and the University of Córdoba. My co-authors today are Antonella D'Alessandro, Austin Doney, Enrique Garcia Macias, Simon Laflamme and Rafael Castro Triguero. The aim of this work is to introduce a novel approach to structural health monitoring of civil structures that is based on self-sensing structural materials and sensors. So I will start with the motivation of the work and then I will spend most of my presentation dealing with the topic of smart concrete. That is a technology of which I will first introduce concept and fabrication and then the fundamentals of micromechanics modeling and finally laboratory applications. Then I will talk a little bit of a new concept that we have introduced within this collaboration in the last couple of years, that is that of smart bricks. Again, I will introduce concept and fabrication and then laboratory applications to paradigmatic structural elements and finally conclusions. So let's come to the motivation of the work. The research I'm presenting is framed in the field of structural health monitoring, which refers to all those technologies that try to use the information provided by sensing systems installed over a structure to understand what's the state of the structure and to possibly detect and locate a damage forming in the same structure. Of course, the application is that of anticipating major collapses and providing information useful for an optimal organization of maintenance and retrofitting strategies with applications on aging infrastructure networks as well as cultural heritage structures, for instance, exposed to the seismic hazard. Applications of SHM in the field of civil engineering are, however, still limited, and one of the most important challenges that, in our opinion, are limiting such applications is what we call the scalability challenge or the scalability issue. With this term, we refer to the circumstance that sensors used for SHM are typically very small compared to the large sizes of the structures being monitored, with the consequence that the damage detection and localization task becomes more and more difficult as the size of the structures increases. One possibility of overcoming this issue is that of going towards self-sensing structures and self-sensing systems. A self-sensing structure is essentially a structure made of a special material that is itself a sensor. So the material can provide information on its state of strain and direct information regarding the formation of a crack or a damage. In this slide, for instance, I show you an example referring to a self-sensing pavement that is a road pavement made of a special smart material that is able to sense the presence of a vehicle and to weigh in motion this vehicle, providing information that can be, of course, used for a fatigue evaluation of the pavement itself or fatigue evaluation of the substructure, for instance, a steel bridge, and for understanding what is the state of stress in the substructure and so on. So in this research we achieved this smart property into concrete and clay bricks by doping these construction materials with electrically conductive nano-inclusions. In particular, we'll see nanotubes, carbon nanotubes that create conductive networks inside the materials in such a way that the materials themselves become conductors. This way we achieve this smart concrete and smart brick that are self-sensing in the sense that they can output measurable changes in their electrical properties under application of an external mechanical input and particularly when they are strained. This information can be easily processed for SHM purposes for a direct crack detection, so therefore solving the scalability issue I was mentioning at the beginning. So let's come to the smart concrete technology. The idea of smart concrete is actually not new. It was early proposed by Deborah Chung at University of Buffalo in the early 90s, and in recent years this topic has received a considerable attention with a lot of scientific papers devoted to smart concrete. Smart concrete essentially is a concrete with dispersed electrically conductive nano-inclusions such as nanofibers or carbon nanotubes that create conductive networks that make the overall composite composite become an electrical conductor. What is very important here is the proper dispersion of the nano-inclusions or the nanofibers, which needs to be achieved with suitable fabrication procedures, as we will see in the next slides. But if the dispersion is good, then we can achieve a very nice percolation-like behavior, as shown on the top right diagram of this slide, where the electrical conductivity suddenly increases when the amount of nanofibers or nanotubes or nano-inclusions reach a critical threshold that is in fact called the percolation threshold. When the material is at percolation, it's not only a good conductor, but it's also a very nice strain sensor. So for instance, if we measure the electrical resistance in across 2 points of a specimen using electrodes, embedded electrodes, we obtain a quantity that is very sensitive to the strain. So if we apply a uniaxial compression load to the specimen and we induce a uniaxial compression strain, we induce also a reduction in the electrical resistance, and the relative change in electrical resistance is actually very close to be proportional to the uniaxial strain through the coefficient lambda that we call the gauge factor of the sensor. So here you have a few highlights of how we fabricate smart concrete and smart concrete sensors in our lab at University of Perugia. So on the top left you see the fabrication procedure, where we first disperse the nanotubes in water by using tailored chemicals that are called dispersants. Then we improve dispersion of nanotubes through magnetic stirring, and in most of the cases through sonication and mechanical mixing. Then we add the aggregates and the plasticizer to improve workability. We cast the composite into oiled molds, we embed the electrodes, and at the end we have these cubic smart sensors made of cement paste with nanotubes, or mortar with nanotubes, or concrete with nanotubes. On the top right of the slide you see a few pictures of concrete specimens, whereby the white specimens are normal concrete ones, the dark specimens are specimens with nanotubes, where it should be remarked that only 1% of nanotubes are used in this case. So you see how significant is the change in color achieved with such a small amount of nanotubes, which is very remarkable. And then on the bottom part of the slide you see SEM pictures showing the nanotubes creating a very nice network when dispersed in water on the left, and on the right you see the nanotubes creating the network when they are inside the hardened cement matrix. Modeling the behavior of these composites is very important, especially to properly relate their electrical response to their state of strain. To this purpose, we have recently developed a nice micromechanics framework that is able to predict the overall properties of the composite, such as the elastic tensor and the electrical conductivity tensor, through an homogenization approach. This method goes effectively from the nanoscale, so modeling the single nanotube and its interface, to the microscale, accounting for the orientation of the nanofibers or the nanotubes, to the macroscale, considering a representative volume element with a certain amount of dispersed nanotubes. In this framework, we have considered peculiar aspects of these materials, such as the tendency of nanotubes of agglomerating into bundles that have a shape that is similar to the one shown in this SEM picture, so the typical shape of an ellipsoid, and also we take into account that the nanotubes are not straight, but rather they are bended and they can assume curved shapes. With this framework, we are, what is most important, we are able to model properly the strain sensing capability of the material, which means the change in electrical properties under application of a mechanical strain. As we have shown in previous work, we can we can identify three main mechanisms that govern this piezoresistivity. The first one is the change in volume that causes reorientation of the fibers, which is taken into account through the so-called orientation distribution function. That is 1 when the nanotubes are uniformly and randomly oriented, and gets quantities and gets values that are different from 1 when the material is strained. The second mechanism is the change in conductive networks that is due to a strain. So, for instance, in strained conditions, there is a lower or higher probability of formation of conductive networks for a given amount of nano-inclusions, depending on the material being stretched or compressed. And also, the third mechanism is a change in the tunneling resistance, so the resistance with which electrons jump from one nanotube to the next one, the change in tunneling resistance that is due to the applied strain. So here we see some results of the application of the proposed micromechanics framework. On the top you see results referring to cement paste with carbon nanotubes. In the middle part of the slide you see results referring to cement mortar with nanotubes, and on the bottom part of the slide you see results of concretes with carbon nanotubes. So on the left, the diagrams on the left show you gauge factor against the amount of nanotubes in the composites, and on the right you see the overall electrical conductivity of the composite against the amount of nanotubes. With the different lines you see results referring to different values of the conductivity of the nanotubes, and with black squares you see experimental results achieved in our lab. So what's very important from this result is that both theory and experiments confirm that there exists an optimal amount of nanotubes that corresponds to a maximum gauge factor of the material, and this amount of nanotubes, this optimal amount of nanotubes, is close to the percolation threshold. It's also notable that the theory can interpret quite well the experimental result. So here let's come to the application of this smart concrete to manufacture strain sensors to be embedded into reinforced concrete structural components. On the top left of the slide you see typical cubic sensors that we fabricate in our lab. They are typically 5 centimeters per 5 centimeters per 5 centimeters, and they have 4 mesh electrodes that are embedded inside. And the reason why we have 4 electrodes is that we want to measure the electrical resistance with both a 2-probe or a 4-probe configuration. On the right pictures of the slide you see sensors installed in an element before casting of concrete. Here we see results of the application of these sensors, and in particular results of these sensors being tested in axial compression machines in the lab. On the top right of the slide you see measured strain through strain gauges attached on the sensor's faces under the application of triangular loads, and corresponding relative change in electrical resistance in blue. You clearly see that there is a very good correspondence between strain and electrical response, which is also the case on the bottom right when applying dynamic loads, so sinusoidal loads with increasing frequency. On the left you see the strain measured by strain gauges in a typical test with triangular loads, as well as the strain estimated by using the electrical output from a smart concrete sensor in red. And you also see that the relationship between change in resistance and strain is actually linear, very much linear, as we assume in a very simplified model. What is also interesting is to investigate the amplitude of the response in terms of relative change in electrical resistance as a function of the mechanical frequency of the load acting on the sensor. In this case, this that is called the frequency response function of the sensor, is typically a function that can be slightly increasing or slightly decreasing with the applied frequency, and we will see how this behavior can be justified in the next slide. So here we see the application of the sensors when embedded into a reinforced concrete beam arranged in the lab. So on the top right you see what happens when a person steps over the beam and then steps out from the beam, and this test is repeated 4 times. In red you see the response measured through a strain gauge attached to the cement-based sensors, and in blue you see the response in terms of electrical current of the sensor placed at the mid-span. So clearly you see that with the cement-based sensors you detect the loading and unloading of the beam in a very clear way, and this is repeated and this is valid for all the 4 times that the load is applied to the beam. Then you also see the results of a test with hitting the beam with a hammer in random locations over the beam. You see in red the measurement of a strain gauge, and you see in black the measurement of a smart concrete sensor at the same location of the strain gauge. If we take a detailed view of a single hit, you clearly see that the time series of the measured strain is very well superimposed to the time series of the electrical output of the cement-based sensor. Also noticeable is that if we take the power spectral density of the signal acquired by the strain gauge and by the smart concrete sensor, the power spectral density have a leading peak that is exactly at the same frequency of about 64 Hz, which allows to conclude that these smart concrete sensors are suitable to be used as vibration sensors, at least for modal frequency identification in reinforced concrete structures. Another important aspect in modeling the behavior of these sensors is being able to reproduce their time response. So in this case, when time is involved, a modeling approach based on lumped circuits, lumped electrical circuits, is probably the most suitable method. So in this slide you see the comparison between a typical model used in the literature, where the sensor is reproduced through an electrical resistor whose value changes with the applied strain, placed in parallel with a capacitor that reproduces the dielectric behavior of the material, and then of course there will be some contact resistance to close the circuit. While on the right you see a more advanced model where we also add a third branch to the circuit, and that branch reproduces the piezoelectric behavior of the sensor that we have shown is present in these materials. So essentially, when the material is loaded, a little bit of voltage develops in the material itself. So the material is not only piezoresistive, but it also has some piezoelectric behavior, and this is introduced in the third branch of the model. We have shown in previous work that with this improved model we can better reproduce experimental results relating to the response of the sensor under application of a mechanical loading of different frequency. But most of all, this model is able to reproduce the possible increase in the amplitude of the response with increasing frequency of the mechanical load. So essentially, the previous model, the simpler model on the top, is associated to a response whose amplitude decreases with increasing mechanical frequency of the load. Instead, if we apply some if we introduce some piezoelectric behavior of the sensor, we can achieve an amplitude of the response that increases with increasing frequency of the load, which sometimes we observe in the experiments. Also very notable is that a similar model is able to reproduce the appearance of superharmonics in the response under an harmonic loading, which is also something that we get from experiments, as shown in the diagram on the bottom right of the slide. So let's now come to a second way in which smart concrete can be used in structural health monitoring. In particular, in this case, we do not want to use smart concrete to manufacture strain sensors, but rather to fabricate structural components that are fully made of conductive concrete. In this way, for instance, we could fabricate a local joint between a beam and a column, or we could build the rebar cover in a critical location of a structure. This concept can be leveraged for damage detection, for instance, by trying to reproduce the electrical behavior of the material through a mesh of electrical resistors, as shown in the top left of this slide, whereby we can try to identify the values of these resistors by matching the experimentally measured electrical response of the material. And when there is a damage in the material in the form of a crack, then we are able to see this damage in the form of resistors with very high resistance. So the first problem that we have in applying a similar concept, however, is that of eliminating the time drift in the electrical response of these materials that is due to the polarization, so the charge accumulation under a constant electrical field. To overcome this aspect, we have proposed recently a biphasic DC measurement approach, whereby the input we give to the material is not a steady input, but rather it's a square wave voltage input with 50% duty cycle, which means that we apply a voltage that is alternating negative and positive, so that the material never charges, or at least charges and discharges every period of the square wave. As we see in the diagram on the bottom right, in this way, we can eliminate the time drift that we see in the resistance versus time plot in the case of direct current configuration, but which we don't see in the case of 1 Hz, 2 Hz, and 5 Hz, and so on, square waves. So, since we are able to achieve steady voltage drops across an element made of smart concrete, we are also able to detect changes in these voltage drops, for instance, following the formation of a damage. And here, for example, I show you the application to a small beam, where we give this square wave voltage input across 2 electrodes, and we measure voltage drops across all pairs of electrodes. We see that voltage drops are larger in correspondence with external electrodes, that are those that carry the electrical contact due to a local contact resistance, and they are of the same order of magnitude for the remaining pairs of electrodes. Clearly, when we apply a damage, as we see in the third diagram, we have a change in a voltage drop, and in particular when there is a damage across in a section between 2 electrodes, we have an increase, a local increase in electrical resistance, which means for a constant electrical current, an increase in the voltage drop across the 2 electrodes. And this increase grows very well and very nicely with the length of a cut, for instance, when artificially damaging the beam. So we can conclude that this approach of locally measuring the electrical resistance of the material, or the voltage drop under an external voltage input, is feasible for detecting and locating a damage. To demonstrate this more in details, here is another experiment referring to a small beam made of cement paste with carbon nanotubes, reinforced only with longitudinal reinforcement to anticipate a cracking in shear, and subject to a 4-point bending loading condition. On the diagrams on the right, you see the change in voltage drop as a function of the applied load for different sections, for different pairs of electrodes along the beam. What we see in these results is that in a very initial part of the diagram, we have increases in voltage drop with increasing load, and those are essentially due to the deformation that the load determines in the material, and here what dominates is the tensile strain that results in a local increase in electrical resistance because the electrodes are in the bottom part of the beam. And then at a certain point, when a damage forms, a shear crack starts to form outside of the region where we have the electrodes, we have changes, sudden changes in the voltage drops across different sections of the beam. So these changes clearly highlight that something has happened in the beam, which confirms again that a similar approach based on a resistor mesh model can allow damage detection and localization, leveraging the electrical conductivity of the material. Here is another example conceived to demonstrate the possibility of detecting damage in smart concrete structures. The example consists of a smart concrete plate, again made of cement paste topped with multi-wall carbon nanotubes. We have put this plate on a device that allows to apply hammer hits with controlled energy to reproduce a certain number of hits, all of them having more or less the same energy. On the plate we have several contacts embedded, as we see on the top right of the slide. We apply a voltage input through a square wave across two electrodes, and we measure voltage drops across all remaining pairs of electrodes. Again, we try to apply a resistor mesh model as shown on the bottom left of the slide, where the red lines are the resistors, and we try to identify the properties of these resistors by matching experimental and model responses in terms of voltage drops. Here we see the results of application of an optimization procedure to identify those resistor properties by solving in an approximate way the inverse problem of identification. And in particular, we show on the bottom right of the slide, we show on the upper diagram the map, the contour plot of the identified resistor values for the undamaged plate, where of course we see that there is some difference from one point to another, probably due to a different quality of the dispersion of the nanotubes and possibly associated to a slightly different moisture content in the material. But after application of 100 hammer hits, the plate is damaged, and in particular there are 3 points of most prominent damage: the impact point in the center, a damage on the back side, which we don't see from this picture, but it's indicated by a black dot, and another damage that's a sort of spalling on the bottom part of the plate. And clearly in these regions we have a local increase in the values of the properties of the electrical resistors that we achieve after solving the inverse problem. So what we can conclude here is that a resistor mesh model like the one proposed can allow a damage detection and localization in a smart concrete structural component such as a plate. So to end this presentation, I would also like to extend the concept of self-sensing structural materials and sensors from the field of reinforced concrete structures that we have seen before to the field of structural masonry buildings. So the idea is that of fabricating smart clay bricks, which are smart bricks able to detect and to measure the strain within the masonry. Of course, the vision is that of inserting a few of those smart bricks inside critical locations of a structure so as to anticipate any change in the structural behavior, detect the formation of cracks and a change in the loading path within the structure, and possibly detect the damage at its early stage. The idea of achieving a smart brick is similar of that of smart concrete, but here there is a big challenge of using the proper doping that have to be resistant to the very high temperatures reached during the baking phase. So we need electrically conductive inclusions that can resist about 1000 degrees Celsius. And at this preliminary stage, we propose to use, since carbon-based particles are not suitable in this case, we propose to use titania, so titanium dioxide particles that that can improve the mechanical properties of the smart bricks and can also increase its electrical conductivity. In the SEM picture in this slide, you see the titania particles after burning inside the clay matrix. So here you see some example of actual compression tests on smart bricks, where you see the application of a triangular load, and again the electrical response of the sensor using the biphasic voltage approach that we have seen before is very much correlated with the load and with the measured strain. What is notable is that with black you see normal bricks. Normal bricks already exhibit some piezoresistive behavior, while nanocomposite clay bricks with red lines, they are a little bit worse in terms of linearity, in particular because when they are very high sensitive, they start to exhibit some hysteresis in their response, but they are able to recover the initial value of the resistance after unloading, as you see here, where 5 normal bricks and 5 nanocomposite bricks have been tested. Overall, experiments have shown that in the case of a smart brick, a model that assumes that the relative change in electrical resistance is essentially proportional to the volumetric strain is feasible and reasonably applicable, so that the brick is sensitive regardless of the orientation of the load with respect to the electrodes. This model is now being validated through a micromechanics approach, which I will not show you here, but is suitable for first level investigations. So here you see a demonstration application of the smart brick idea. You have a small masonry wall with 3 smart bricks. This wall is placed in an axial compression machine, and you clearly see on the top right of the slide that if we apply a vertical load to this wall, we have a change in the electrical resistance of the smart bricks that more or less tracks the intensity of the loads. It's important to notice that in this case, when we apply an electrical voltage across 2 electrodes of a brick, actually we are measuring not only the electrical properties of the single brick, but we are actually measuring the electrical properties of the whole wall. In the experiments you have in the bottom part of this slide, you see voltage measured in the different electrodes in the wall, so in different bricks in the wall, by applying a voltage in the 2 contacts of the brick placed in the middle, and you clearly see that the lines of equal voltage tend to go across the whole wall, which means that current flows not only in the smart brick but also in the neighboring brick. So in this example, we have a compression load that we can apply with some eccentricity with respect to the centroid of the cross-section. And we have 3 smart bricks that are able to provide relative changes in electrical resistance proportional to volumetric strain. So of course, we can model this system with a simple beam model, assuming the possibility of having cracking in bending. And we can predict what's the expected value for this relative change in electrical resistance for each brick. So from the theory, we would expect the results reported with red lines. You see here the cases of an applied load of 20 kilonewtons, 50 kilonewtons, and 70 kilonewtons. So you have essentially a linear variation of the strain with the distance from the center of the cross section, for example. And of course, with in the experiments, you see results that are not perfectly matching with the analytical ones because of the approximation of the analytical model. But at least we see the same trend, where those results are expressed in the form of normalized changes in electrical resistance, where the normalization is with respect to the change in electrical resistance that we have for centered loading condition. So in blue you have the case of a left loading, and in green you have the case of a right loading. What we should notice here is that when we have a load of 20 kilonewtons or 50 kilonewtons, the experimental results are very similar to each other. So as we expect, since those are normalized changes in electrical resistance, we don't have dependence on the applied load. We are in the elastic range. But when the load reaches the value of 70 kilonewtons, we have clearly a deviation in correspondence of brick number 3 for the left loading case from the previous reading, and also a large deviation from the analytical prediction. This is due to the fact that at this loading condition, the wall has started to fail in compression in the region under the load, and the vertical crack has formed in the masonry. So the formation of the crack has resulted in a clear change in the response of the bricks, and we can therefore conclude that the bricks are suitable for being used for strain sensing as well as damage detection in a masonry structure like the one shown. So to conclude with this presentation, I've shown you the concept of embedded smart concrete sensors that can be a durable solution for strain monitoring of reinforced concrete structures. We have shown that micromechanics modeling approaches as well as lumped circuit methods can be very effective for predicting the response of these materials and sensors. We have been able to eliminate the polarization issue in the response of these materials under application of a constant, under application of an external electrical field, and this has allowed to achieve steady measurements that can be used for direct crack detection in smart concrete structures. Also, we have introduced the smart bricks concept that allows to monitor strain in structural masonry and permits damage detection. So overall, we can conclude that smart concretes and smart bricks can potentially improve the current state of development of SHM by overcoming what I called at the beginning the scalability issue in structural health monitoring when applied to civil structures. With this, I thank you very much for your attention, and I would like to acknowledge the last scientific project that we have obtained and that is funding this research. This is a project funded by the Italian Ministry of Education, University of Research, whose title is Smart Brick, Novel Strain Sensing Nanocomposite Clay Brick Enabling Self-Monitoring Masonry Structures. This project is gratefully acknowledged, as well as the other sponsors of the research. Thank you very much for your attention.